Okey, Assalamualaikum dan salam sejahtera kepada semua. Our class for Fluid Mechanics BNJ 20203 continue dengan our last chapter, which is chapter 7, which is pumps. So bila kita cakap pumps, especially rasanya in chapter 6, flow analysis in pipes, kita dah introduce sedikit kan pasal pumps. So dekat sini kita akan, untuk chapter ni kita akan lebih fokus ataupun lebih detail, kita akan discuss pasal pumps. So bila kata pumps ni, apa kegunaan pumps kepada sistem, dan how pumps can be relate dalam piping systems, and then types of pumps, macam mana kita nak dapatkan pumps yang sesuai untuk satu-satu piping systems tu. Lepas tu macam mana kita nak classify the efficiency of the pump itself, and so on so forth lah. So in this chapter kita akan fokus banyak pada pumps. Okay, so before kita start, saya nak recap balik sebelum ni kan kita, bila kita kata energy equation is actually a Bernoulli equation lah. Bernoulli equation, kalau siapa-siapa ingat lagi, adalah P over rho G plus V squared over 2G plus Z kan. Ini on the left hand side. Belah kanan pun sama juga, P over rho G plus V squared, kejap, V square over 2G plus Z. Tapi kalau belah sini adalah dekat position 1 lah, P1 V1 Z1, ni P2 V2 Z2. And if let's say kita kata dalam satu-satu sistem tu kita kena consider pumps kita kena tambah dekat sini, which is H pump. Sebab pump ni dia apa? Dia add energy. Dia a kind of losses, tapi dia bukan losses tau, dia add energy to the system kan. Dia terbalik. Dia kalau losses tu kita kena tambah belah kanan. Okay, contoh HL lah, yang mana kalau dekat chapter 6 kita dah belajar, kita ada major losses dengan minor losses kan. Major losses ni disebabkan all the friction lah kan, surface friction. Lepas tu kalau minor ni disebabkan dia ada orientation of the pipe itself, and then ada entrance punya losses, exit punya losses. Lepas tu kalau dia ada additional item such as valve, apa tu semua kita kena consider dekat minor losses. And nak highlight balik, kalau pumps kita add energy. Okay, so jangan confuse what is this and what is this. So in this chapter we are only going to consider this part. Okay, however in the question later on, dia disebabkan bila kita kata pump ni is one of the piping system, ada dalam piping system. So equations boleh relate dengan piping. Okay, dia boleh guna pakai, kita kena guna pakai permasalahan di chapter 6 untuk selesaikan pumps punya masalah juga. Cumanya untuk pumps kita ada additional items that we need to consider lah, in which we will discover in details later on in this chapter. Okay, as for introduction, what is pump? Pump is a generic term for any fluid machines that add energy. Macam saya cakap tadi kan, dia akan add energy to the system. Okay, some authors call pump as an energy absorbing devices. And sebab apa? They add energy since energy is supplied to the system, and then they transfer most of the energy to the fluid via a rotating shaft. Kalau kita tengok sini kan, ni contoh bila kita add on pump. Pump kalau bentuk dia macam ni alright, dia macam dia akan ada add on energy ke dalam sistem tu, yang mana in the end the energy dekat bahagian out ni akan lebih besar daripada energy in ini. Okay, and thus it will increase the fluid energy, kan, seperti yang saya cakap ini, and it is usually felt as an increase in pressure as well. So means that P out ataupun P2 will be more than P1, ataupun P1 is lesser than P2. That is what function of pump. They add on energy to the system. Okay, so apa yang keluar dekat belah kanan ni akan ada energy yang lebih daripada kiri, disebabkan ada this rotating shaft yang akan provide all the energy. Okay, so kalau tengok figure 14.3 ni, this is an example of a pumps in which can be divided into fan, blower and compressor, and the characteristic of this pump can be classified further into pressure drop or pressure rise, and also volume flow rate. Yang ni you guys can take a look later on, apa perbezaan antara fan, blower and compressor. These are different types of pump lah yang available. Okay, so next adalah turbines. Nak senang cerita, turbines ni adalah terbalik daripada pump. Is the function is the other way around, in which turbines are the energy producing devices. And kalau kita tengok ini gambar dia, kan, dia punya bentuk pun terbalik. Okay, kalau kat sini apa kegunaan turbine ni? Dia extract energy, kan. Tadi add energy for the pump, tapi untuk turbines dia extract energy from the fluid and transfer most of the energy into mechanical energy output, typically from in the form of a rotating shaft, kan. Kita tengok sini dia punya arrow keluar, kan. So kalau kat sini kita nak dapat tengok dia terbalik, in which energy in dekat sini lebih besar daripada energy out, kan. Dia bentuk dia dah terbalik daripada pump. Okay, which means that the fluid at the outlet of a turbine suffers energy loss, typically in the form of a loss in pressure. That is why P2 can be considered much lesser than P1. So you guys need to understand what is the differences between pumps and turbines. So they are opposite. Okay, so next kita focus on pumps. So bila kita kata pumps ni, there are many types of pumps in which can be classified further into dia punya classification lah, and this is based on pumping action. Dia berubah based on sama ada dia positive displacements atau dynamic, and then based on the orientation dia juga, kan, sama ada dia vertical punya bentuk atau horizontal, and then based on number of stages, banyak stage ke, single stage ke, and then based on types of shaft sealing, based on speed, based on location, its location dalam piping system tu kat mana, and also based on prime mover. Okay, so there are many classification of pumps that need to be considered. So in details, you guys tak perlu tahu banyak sangat. You guys kepelbagaian pumps ni pun you guys boleh tengok dekat YouTube lah. So in this chapter kita bukannya nak fokus sangat kepada perbezaan pumps. Cukuplah sekadar few yang saya akan tunjuk kemudian. Yang lain-lain tu, as long as you guys know that there are variety of pumps, that it should be enough. Okay, so kalau kita tengok dekat sini, kan, kita ada dynamic, kita yang ni benda-benda yang penting yang kita fokus sikit kat sini. So kalau kita tengok sini, based on dia punya pumping action, so kita ada dynamic and positive displacement. Positive displacement, sekejap lagi saya next slide kita akan tunjuk lebih detail. And then for dynamic, kita ada contoh centrifugal. Centrifugal ni agak popular, okay, bentuk dia yang macam siput tu. Okay, sebab kita ada impeller kat sini, dia akan ada inlet dekat sini, and then outlet dekat sini, kan. Kalau ini paling mudah korang tengok cerita turbo, kan. Okay, so bentuk turbo tu macam mana, so ini contoh lah, okay, for a centrifugal pump. Untuk axial pump pula, dia lebih pada straightforward lah, okay, inlet and outlet. Lepas tu kat tengah ni impeller dia bergantung lah kepada bentuk dia. Alright. So okay. Kalau kita tengok dekat sini kan, bila cakap pasal positive displacement ni kan, dia pun ada dia punya bentuk-bentuk juga, sama ada rotary ataupun reciprocating. Okay. So bila rotary ni pula ada bentuk-bentuk gear dia, gear, screw and so on so forth lah. Okay, banyaklah perbezaan dia dari segi dia punya classification atau alright. So this is the positive displacement pump. So what is a positive displacement pump? So positive displacement pump ni adalah it can be considered as a one way direction. So dia punya pump tu bergerak dalam satu direction sahaja. Okay, and these are examples of positive displacement pump, in which kalau kita tengok yang A ni, yang the first one is a positive ataupun a flexible tube peristaltic pump. Okay, so kalau kita tengok pump ni is actually kegunaan dia banyak dalam medical. Okay, it can be considered as a heart lung machine. Okay, and usually is used in for example in open heart surgery. Sebab apa? Kalau kita tengok bentuk kat sini, ni dia punya mechanical system. So kalau dalam medicine, dia punya laluan ni akan dilalu oleh darah lah basically kan, sebab kita consider dalam medicine kan. So darah dia akan lalu sini, dia akan keluar sini. And kenapa this type of pump is usually used in medical? Disebabkan bentuk mechanical system dia yang menyebabkan dia lebih sesuai diguna pakai dalam medicine. Okay, so sebab apa? Sebab bila darah lalu, contact dia dengan mechanical system kurang as compared to other kan. Kalau kita tengok kat sini kan, bentuk dia dengan kat sini bentuk dia macam mana kan, dengan ada gear punya gigi-gigi ni kan. So if let's say bentuk macam ni, less contact dengan mechanical systems means that the blood, the darah, dia akan molekul dia akan terjaga lah basically. If let's say kalau bentuk dia macam ni, macam gear ni, dia akan menyebabkan molekul-molekul darah tu pecah, and then pecah akan menyebabkan gumpalan, and then which is not good lah for the patient. Okay, that is why this type of pumps is usually used dalam medicine. Okay, this is an example of a positive displacement pump lah. Okay, kalau kita lihat dekat B ni pula, B dengan C ni lebih kurang sama je. Yang berbeza dia adalah dia punya bentuk ni. Ini adalah 3-lobe rotary pump, and then we have gear pump kat sini, and then the last one kita ada double screw pump. Okay, in which kita tengok perbezaan dia adalah dari segi mechanical system dia. Okay, tapi dia punya objektif sama je, dia provide one way direction punya pumping system. Okay, kita continue. Di sini ada sedikit penerangan lah mengenai head. Rasanya head ni pun kita dah jumpa banyak dalam chapter lepas lah. What is a head? Head is actually a term for expressing the height of a water column. Okay, so kita juga boleh convert head kepada pressure head lah, guna rumus P equals to rho GH, di mana H ni kita substitute dalam pressure punya equation, and then kita will get the pressure head. Okay, and then what is suction head? Suction head is actually the head at the pump inlet suction location. Okay, so dekat sini contohnya sini ada pump, sini dekat inlet dia lah. Okay, this is what we call as a suction head. And then this suction head kita boleh pecah kepada dua, static suction head dengan static suction leaf. So what are the differences? So kita go by the definition first. Static suction head is actually the suction head under no flow static conditions equal to delta Z from the feed reservoir to the inlet. Kalau kita tengok kat sini kan, static suction head contohnya, sini ada dua gambar, sini satu, sini satu, yang pertama, yang kedua, dan kita tengok position of the pump. Okay, so untuk the first one, this is called a static suction head, which is more than 0. Okay, alright. So if let's say dia delta Z equals to 0, so means that the pump location, contoh yang ni pump dengan inlet dengan outlet adalah sekata. Okay, this is when delta Z is equal to 0. So if let's say the position of the pump is much lower, so this would be the the situation in which static suction head will be more than 0. And then there are the second case in which kita consider as a static suction leaf, which is actually the opposite of the static suction head, and is sometimes used when the pump inlet is above the source. So kita nampak the pump inlet also adalah lagi tinggi daripada dia punya source. Okay, so yang ni sometimes kita boleh kata as a positive static suction leaf ataupun negative static suction head. Okay, dia adalah the opposite of the static suction head. So kita tengok sini ada dua So don't be confused on these two definition. So dia sama je. If let's say you want to use a static suction head, can either cakap positif or negatif. If let's say macam ni, dia positif lah. The first condition ni dia positive suction head. Kalau kat sini negative suction head ataupun positive suction leaf. Alright. Okay, next kita jumpa lagi satu term which is called the net positive suction head. Okay, so what does it means? So bila kita kata net positive suction head ni, actually dia boleh pecah kepada dua. Tak apa, yang ni dia consider yang ni dulu So net positive suction head available. What does it means? Okay, so dia adalah suction head sama juga macam yang sebelum ni. Cumanya kat sini kita akan perkenalkan this new item, which is what is available. So it is by definition, it is the difference between the inlet pump, between the pump's inlet stagnation pressure and the vapor pressure head. So ini rumus yang kita kena ingat. Dia kalau kita tengok dekat sini, dia lebih kurang macam energy equation je. Kan dia ada pressure punya terms and velocity punya terms. Cuma kat sini kan, kalau by definition, it is actually the differences between the pump's inlet stagnation pressure, which is the first term kat sini, and also the vapor pressure head, which is sini, and the differences. Okay, this NPSHA is the theoretical amount of heat, okay, that could be lost between suction and point of minimum pressure without causing cavitation. So this is important. NPSHA ni adalah amount of heat. Amount of heat tu amount of heat lah, okay, that could be lost between suction and point of minimum pressure. Okay, so without causing cavitation. So what is this cavitation means? Alright, so cavitation, kalau kita tengok kat gambar ni, adalah contoh-contoh cavitation yang berlaku, yang boleh merosakkan blade atau impeller pumps tu sendiri. Okay, this is what could be happened if let's say cavitation occurs. So how this cavitation can occur? So it will occur when the local pressure inside the pump is much less than the vapor pressure of the liquid. So maksudnya vapor pressure dalam liquid tu sendiri, vapor pressure dia lebih tinggi daripada pressure dekat pump. So this is called a cavitation bubbles in which the liquid boils locally. Kan bila pressure tu lagi tinggi, dia akan boils. Bila dia akan boils, dia akan keluarkan bubble. Kan bila kita panaskan sesuatu, dia akan keluarkan bubbles kan. So these bubbles will be transported through the pump. Okay, sebab dia pressure lebih tinggi, so dia akan boils, and then this bubble akan transported masuk ke dalam pump to the region where the pressure is higher and causing rapid collapse of the bubbles. Okay, so this collapse of bubble yang dekat dalam pump ni, it will cause sometimes noise, vibrations, and it will also reduce the efficiency of the pump, and most importantly, dia akan damage these impeller blades. Okay, so repeated bubbles that collapse dekat impeller ni, dia akan leads to erosion. Erosion, and also eventually dia akan catastrophic blade failure. Dia akan bagi failure the impeller, the blades or the pumps itself. So in order to avoid this cavitation, we must always make sure that the net positive suction head available must be more or equal to the one that is required. Required kita tak sentuh lagi, lepas ni kita akan sentuh required. So dia ada dua, net positive suction head dengan net positive suction that is required. So to avoid this from happening, kita kena ingat yang available should be higher lah daripada yang required kan. Yang ni kita fikir secara logik lah, nak senang faham. In order to avoid this cavitation, all the bubbles that is trapped into the impeller and cause this catastrophic blade failure, the suction head available must be more, or at least the minimum should be equal to the one that is required. Okay, next, okay, this is the net positive suction head required. Yang ni yang required tu lah. It is actually the minimum value of an NPSHA kan, sebab kita cakap tadi kan, NPSHA must be more or equal to NPSHR kan. So it is the minimum value of NPSHA that is needed to prevent the cavitation. Okay, so usually this NPSHR that is required ni adalah spec yang diset up oleh manufacturer. Okay, and is determined experimentally by pump manufacturers and reported as a function of pump flow and so on and so forth lah. Okay, and okay, ini tak ada apa, ini pun sama juga. To avoid cavitation, always the pumps need to operate NPSHA more or equal to NPSHR. Yang ni kita akan go through lebih detail lah bila kita tengok pump performance curve. Alright, so the maximum allowable elevation of a pump. So yang ni kita nak tengok berapa jauh tinggi Z1 ni daripada this reservoir, daripada inlet kepada pump ni, berapa maximum allowable elevation of a pump based on theoretical knowledge yang kita dah tahu tadi, NPSHA must be more or equal to NPSHR. Daripada sini kita boleh calculate, or kita boleh determine the maximum allowable elevation of a pump. Berapa tinggi pump ni boleh kita position daripada dia punya reservoir. Okay, so rumus yang kita dah tahu tadi kan, NPSHA equals to this. Okay, and then this absolute stagnation pressure kita boleh ganti with this term, in which kita consider this this suction lift, this elevation kat dalam this equation, and then kita minus all the losses juga, and also this kinetic punya terms, and then kita replace balik masuk dalam this equation. Kita akan dapat in the end this. So this is actually the NPSHA, which is this itself must be more or equal to NPSHR. So the one that we would like to determine is the maximum allowable elevation of a pump. Maximum allowable elevation of a pump, which is this the suction lift lah, the elevation of suction lift lah. Okay, ZSL. So macam yang kita nak buat, kita just rearrange so that ZSL is what we wanted. Okay, so just kita rearrange sahajalah. Okay, thus this suction lift must be less than the expression on the left. Okay, so yang ni mesti less daripada ni in order to avoid cavitation, kan? Sebab yang ni rumus dia kita guna, saya ulang banyak kali lah, tak apa is more and equal to NPHR. So dari sini kita rearrange, kita dapat ni. So this ZSL must be less and equal to the left hand side punya terms, so that expression indicates that the maximum allowable suction lift. Okay, berapa maximum elevation of the ZSL can be positioned above the reservoir. Okay. Okay, now let us continue untuk chapter 7 ni. Okay, sekarang kita masuk kepada pump performances. How we describe or kita judge satu-satu pump performance tu. Okay, so for incompressible flow, it is more common if let's say kita guna volume flow rate. Selalunya kita akan guna volume flow rate lah, as compared to the mass flow rate. So what is the apa orang panggil dia punya simbol for the volume flow rate adalah V dot ataupun Q lah. Okay, kita can use either one. Kalau mass flow rate is M dot. Okay, so in the turbo machinery industry, this volume flow rate is sometimes called as a capacity. So this volume flow rate can be also considered as capacity, and is simply mass flow rate divided by fluid density. So this is the equation lah. Okay, the volume flow rate equals to the mass flow rate divided by the fluid density. So yang ni sebenarnya rumus ni daripada rumus boleh diterbitkan daripada rumus density itself lah, kan? Density equals to mass over volume, kan? So kita rearrange so that we can get the volume flow rate equals to the mass flow rate divided by the density of the fluid itself. And the performance of a pump is characterized by its net heat. Okay, net heat, which is defined as the change in the Bernoulli heat between the inlet and the outlet of the pump. So basically nak dapat the net heat ni, this is the net heat equals to outlet punya energy minus the inlet punya energy, and the equation is sama lah, and P over rho G plus V square over 2G plus Z minus dekat inlet punya energy. Okay, this is the net heat yang kita guna pakai, okay, untuk assess the performance of a pump. Okay, ni contoh contoh performance of a single stage fixed speed centrifugal pump. So ini contoh of pump performance punya graph. Okay, so kalau kita tengok dekat sini, the axis is the volume flow rate, okay, or also known as the capacity lah. Okay, the capacity or the volume flow rate. Okay, daripada kosong sampai ke maksimum. So kalau y axis ni bergantung kepada karakteristik yang selalu kita guna pakai adalah the horsepower. Okay, this is the curve for the horsepower, and then we also have the head. Okay, head tu, dan juga efficiency of the pump. Okay, this is the common three characteristic of the pump yang kita boleh assess dalam satu-satu pump performance punya graph. Okay, so Ni contoh, as valve is open more, ni valve bila valve ni kita boleh consider different condition lah. Maybe 1/3 open, maybe 2/3 open, ataupun fully open. Fully open adalah 3/3 lah. Okay, so as valve is open more, the volume flow rate or the capacity increases and the total dynamic head will decreases. Betul tak? Contohnya kan, the volume as a valve open, this capacity akan meningkat kan. Cuba kita tengok what happen to the head. Head akan berkurang as the inlet the valve is open. So maksudnya kalau macam at 5000 volume flow rate ni means that the valve is fully open lah. Bila fully open tak ada head. Okay, bila dia close dia ada 70 head, 70 feet as dia punya head value. Okay, ini yang cuba nak diterangkan lah the relationship between head and capacity. And then dia ada jugalah efficiency dan horsepower. Usually untuk satu-satu pump tu kita tengok efficiency paling tinggi lah. Efficiency paling tinggi, lepas tu at berapa volume flow rate dia kan, sebab kita nak guna pakai satu-satu pump tu at its highest efficiency lah kan. Alright, so okay, and then this is all the important characteristic ataupun parameter yang kita boleh guna pakai untuk kita nilai the performance of a pump. Okay, so kalau tengok, kita contoh tengok dekat figure belah kanan ni kan, kita ada use of manometer untuk kita dapatkan the value of head, and then kita ada the horsepower that is provided to the pump. Okay, so what else here? So kita go through satu-satu. The net head of a liquid pump is H equals to the EGL out minus the EGL in. Okay, yang ni the EGL is energy grade line. Okay, dia sama macam rumus yang dah diterangkan tadi kan. Dia guna energy equations at the outlet minus at the inlet. Kalau kita tengok dekat gambar sebelah ni pun kita boleh nampak EGL in dengan EGL out kan, tinggi dia dengan tinggi dia. Okay, alright, so dia adalah daripada datum plan, which is Z equals to 0, and the value is also sama macam value H yang manometer kita dapatkan, which is this one. This is the value of net head. Okay, EGL out minus the EGL in. And there is a special case in which if let's say D out equals to D in and Z out equals to Z in, the net head is simply equals to P out minus P in over rho G. Okay, so actually benda ni kita boleh refer balik kepada this equation, because if let's say D out over D in means that this item can be cancelled out. Betul tak? Sebab apa? Sebab kita tahu Q equals to AV kan. So V kat sini kita replace by apa? Q over A. This A is actually pi R squared, in which this R squared is actually D over 2 kan. Since D is equal, so these terms and these terms is cancel out sebab sama kan. So Z out equals to Z in, so means this item can be also cancel out. That is why what's left is net head equals to this P at outlet minus inlet over R rho G kan. So this is when a special case means that this diameter and also this diameter is the same, and also dia tak ada perbezaan Z out and Z in lah. Okay, Z out and Z in means that this one and this one, instead of dekat sini, dia dekat sini. Okay, no elevation at Z direction. Okay, this is special case lah. Alright, and then we also have the water horsepower equals to m dot the mass flow rate time G time H, in which kita boleh mass flow rate ni tukar kepada volume flow rate lah, biasalah volume flow rate kan equals to mass flow rate over rho kan. So kita replace yang ni dengan yang ni. Okay, this is to get the horsepower or water horsepower, and then the brake horsepower equals to what is given to the pump, which is from the shaft, which is equals to omega T shaft. So omega is the rotational speed, radian per second, and also torque of the shaft itself. Usually if let's say in the question, this will be given lah. Alright, and then how to calculate the pump efficiency is equals to this water horsepower over the brake horsepower, kan? Over the brake horsepower means that apa yang diberi tu sepatutnya the maximum lah, kan? Water horsepower ni apa yang dah diguna pakai dalam pump tu. Okay, so this divide by this, kita dapat the efficiency of the pump. Water horsepower divide by the brake horsepower. Okay, this is how we actually calculate the efficiency, kan? So in which represent this graph lah, tadi tu. Okay, okay, horsepower is horsepower lah. Okay, alright, and then this is pump performance curve, let's say in general lah. Okay, so kalau kita tengok dekat graph ni, actually from this graph kita boleh extract banyak maklumat. Okay, so dekat sini kita akan pecah kepada tiga important parts, which sekejap, saya nak guna color apa ni, macam-macam color dah ada. I use this color line set light grey. Okay, so kita akan discuss what happens in the free delivery, what happens at the shut off head, and what happens at this BEP. Okay, at these three location, this one, and this one. So first of all, kita consider at pump free delivery first. So at pump free delivery, okay, yang ni the maximum volume flow rate. Okay, so at pump free delivery kan pasti X adalah capacity ataupun dia punya volume flow rate, kan? Dekat paling tinggi head is 0. H, this one, H will be equal to 0, kan? This blue line color graph, So this flow rate is called the pump's free delivery. So maksud dia at maximum ni pump macam tak diguna pakai lah. Okay, that is why head is equals to 0. So maksud dia free flow, dalam pipes tu. Okay, no flow restriction at the pump inlet or outlet, or no load on the pump, sebab dia free delivery, so no load on the pump lah. So bila no load, no head dekat pump tu. So this is the position where
wait, Daniel,
okay,
how are you two getting?
Okay, next apa lagi dia cakap kat sini? Operating point V is large but H is 0. The pump efficiency is 0 because the pump is doing no useful work. Kalau kita tengok kat sini, tadi kita tengok biru, kan? Ni sekarang kita tengok line hijau. Line hijau is this efficiency of the pump. Kita dapat tengok juga dekat this point, since pump is not working, so the pump efficiency is also considered as 0 at this free delivery punya position. Okay, kan? Alright, so kita dah explain pasal free delivery. So the second part is at the shut off head, which is at this location, this X location. So bila kita tengok dekat sini, at shut off head, the net head that occurs when the volume flow rate is 0. So dekat sini pula dia terbalik, volume flow rate 0, so dia ada maximum head. Okay, and this is achieved when the outlet port of the pump is blocked off. Maksudnya kita tutup, dia tak bergerak pun, so tak ada pengaliran pun yang berlaku. That's why the volume flow rate is equal to 0. So under this condition, H is large, the head is maximum, but V is 0. The volume flow rate is equal to 0, and it is achieved when the outlet port is blocked. Okay, so pump efficiency lagi sekali is also 0 because the pump is doing no useful work. Okay, bila dia tak bergerak tu, pump pun tak function lah sebenarnya, Okay, this is the same condition macam tadi tu kan, dekat maximum flow rate, no useful work is done. At maximum heat and no useful work is done juga kan. Kalau kita tengok graf pump tu, dia macam ni. So at both location the pump efficiency is 0. Okay, so ini pula next kita go through the third position, which is at this BEP. What is BEP? BEP is the best efficiency point. Kalau kita tengok kat sini, the point efficiency yang paling tinggi. Okay, so what happened actually at this position? So at this position, the pump efficiency reaches its maximum value somewhere between the shut off and the free delivery conditions. Okay, and this operating point is called the BEP. Okay, and is notated as an asterisk. So means at this position kita akan dapatkan value heat, kita akan dapat value BHP, and kita akan dapatkan value the volume flow rate. Okay, and then actually this three graph kan, kalau kita tengok kat sini three graph ni, kita ada graph BHP, volume flow rate dengan heat. Okay, no, sorry, the efficiency, the heat and the BHP. Okay, these are called the performance curve. Okay, sama juga macam ni sebenarnya. Okay, jangan confuse. Okay, kita ada efficiency, kita ada heat dan kita ada horsepower. So this is called the pump performance curve, and kita ada this is the efficiency, this is the heat, and also this is the BHP. Okay, and the pump performance curve change with rotational speed. Different rotational speed of course will lead to different performance curve lah. Okay, and this is another important items that you need to understand. And for a steady operating point of a piping system is established at the volume flow rate where H required equals to H available. Okay, so yang ni sama juga konsep macam tadi lah. MPSH A must be equal or more than the MPSH R. Okay, so paling kurang pun H required must be equal to H available, and ataupun H available ni more than the required. Okay, so that in order to avoid last time, avoid cavitation. Okay, so this part pula macam mana kita nak matching a pump to a piping system. Kita ada satu piping system. Piping system kita pula bukannya macam horizontal satu bentuk je kan. Dia bermacam-macam bentuk untuk meet requirement dekat satu tempat tu. Okay, so and in this slide dia akan tunjuk macam mana kita nak match this pump into this piping system. Okay, so a general piping system with elevation, dia mesti ada elevation change, ada major and minor losses, and fluid acceleration. Kalau kita tengok dekat sini kan, elevation mesti ada lah kan, elevation dia. Lepas tu major and minor losses, apa yang kita boleh tengok kat sini. So major losses dia of course daripada friction lah dalam pipe tu. Lepas tu minor losses dia daripada this valve, or also the orientation of these elbow pipes and so on kan. Okay, and also the fluid acceleration. Okay, so in order to find the H pump atau H required, and for the spec of the pump yang ni kan, spec of the pump lah, the H value yang kita nak dapatkan kat sini kan, H required atau H pump tu kan. So apa kita kena buat, kita guna rumus Bernoulli, biasa rumus ni lah juga. Okay, in which untuk yang ni kita dah combine dah sebenarnya daripada rumus ni. Okay, so kita ada pressure terms, the kinetic terms, the elevation, and also the total loss. Total loss ni yang they include major and minor losses. Okay, where we assume that there is no turbine in the system, although that term can be added back if necessary. So if turbine, kita kena consider jugalah. Okay, the equation tells that the useful pump head delivered to the fluid does four things. So daripada equation ni kita boleh discard another 4 important points. Okay, so it increases the static pressure of fluid from point 1 to point 2. Okay, ni point 1, ni point 2. So kita tengok the first term here, the first term on the right. Okay, it increases the static pressure. So if let's say this is point 1, this is point 2, these terms mention that it will increase the static pressure, okay, of the fluid from point 1 and point 2. And then the second point is that it increases the dynamic pressure as well, and dynamic pressure is the kinetic energy lah dekat sini, okay, of the fluid from point 1 to point 2. So what is alpha? Alpha is the coefficient and coefficient for the velocity. Okay, yang ni selalu given lah dalam soalan, alright, ataupun coefficient ataupun correction factor lah for this velocity if let's say it is not perfect kan. Okay, so yang ketiga daripada third punya item lah, it raises the elevation or the potential energy lah kan, of the fluid from point 1 to point 2, and also it overcomes the irreversible head losses in the piping system, which is this one, the head losses. So all these 4 items important in determine the useful pump head or the required head or the pump, the H pump for the specification of this pump later on. Okay, so kita akan guna this equation. This equation is very important, okay, very important in order to determine satu-satu pump tu sama ada dia sesuai atau tak sesuai dalam satu-satu piping system. Okay, semua ni perlu diambil kira, okay, dalam menentukan spec H required for the pump itself. Alright.
Okay guys, before we ended this chapter, I'm going to show you one example of questions related to this topic. Okay, seperti yang saya dah cakap sebelum ni, bila kita kata pump system, dia mesti ada interrelated dengan pipings, kan? So means that chapter 7 and chapter 6 ni means pumps dengan chapter 6 last time is analysis of flow in pipes, kan? So mesti ada interrelated. Dalam satu-satu soalan tu mesti ada kena-mengena yang mana kita kena involve, kita kena participate, kita kena masukkan kedua-dua kefahaman kita waktu flow dalam pipes dengan penggunaan pumps dalam satu soalan yang sama. Contoh untuk adalah soalan ni. So kita go through soalan-soalan ni agak panjang, so it might takes time lah untuk sama-sama kita fahamkan lah. Okay, tak apa, kita go through satu-satu. Okay, so the questions, a local ventilation system which include hood and exhaust duct. So kita ada hood dekat sini, lepas tu ni semua exhaust duct lah. Okay, so yang ni is used to remove air and contaminants produced by dry cleaning operation. So yang ni selalunya kita dapat nampak kat kitchen jugalah, yang mana kita ada hood yang dia nak suck in all the contaminants ataupun bad odors dekat dapur tu kan, selalunya lepas masak ke apa kan, bau-bau tu semua kan dia nak remove kan. So the duct is round. Kalau kita tengok kat sini semua round kan. Okay, alright, and is constructed using a galvanized steel. Okay, material dia bagi with longitudinal seams and with joint every 30 inch or 0.76 meter. Means that panjang this round duct is 0.6 meter. Okay, the inner diameter is given. Okay, the inner diameter of the duct and the length, total length of duct bila kita sambung semua around 13.4 meter. Okay, the equivalent roughness roughness dalam duct tu pun diberi kan 0.15. Roughness apa? Dia punya simbol this epsilon okay, is given. Okay, and each elbow has a minor loss. Loss coefficient given by KL equals to 0.21 and dia diberi juga untuk elbow 0.21 dan kita ada apa? Major and minor losses kan. Yang ni pemahaman kamu dalam chapter 6 sebelum ni, pipes kan. So kalau major ni lebih kepada friction lah, friction dalam pipes tu. Dan yang lain-lain dia adalah daripada minor. Contohnya orientation, orientation of the pipes, and then ada additional term macam valve ke, and then and so on lah. Okay. Alright. So dia diberi kat sini, dia ada elbow punya minor losses sebab bentuk dia macam tu kan. Diberi 0.21. And then what else is given here to ensure adequate ventilation? Dia bagi tahu minimum required volume flow rate for the duct to operate is 600 cubic feet per minute ataupun in SI 0.283 meter cube per second. So dia bagi tahu lah minimum flow rate yang diperlukan at 25 degrees Celsius. Yang ni pun penting Okay. Literature from the hood manufacturer lists that the hood entry loss coefficient is 1.3. Okay, dia bagi satu lagi minor losses which is entry. Dia ada entry losses. Okay, 1.3 and then the damper is fully open. Damper, dia ada damper sini Damper ni macam buff lah. Ni pun losses juga dekat sini. So kita boleh add on kat sini lah. Ada damper. Okay. Juga diberi loss coefficient dia equals to 1.8 and then apa lagi, a centrifugal fan. Okay, dia ada pumps dia ada pumps kat sini fan adalah sejenis pump kan. Alright, with 9.0 inch inlet and outlet diameters is available. Okay, so okay, kepada soalan ni, terus ke soalan dia suruh predict the operating point of this local ventilation system. Okay, and draw a plot of required available fan pressure rise as function of volume rate is and also is the chosen fan adequate. Kan macam saya cakap dulu. Basically soalan dia nak tahu additional of this fan dalam satu sistem piping ni okey ke tak? Kan? Adequate ke tak? Sama ada dia punya operating dengan required tu macam mana? Kan kalau kita cakap dulu last time, in order to avoid cavitation, HA must be more or equal to HR. Kan? So available operating head, operating point dia mesti lebih besar atau sama dengan HR. So HR ni adalah minimum value untuk HA ni. Kan? Alright. So ini sepatutnya untuk soalan ni you guys need to draw this graph lah. This is, kalau semua masih ingat, this is the pump performance curve. Okay, this is given actually. Cumanya kat soalan ni maybe dia tak complete So this is actually given. Kan dia kata kat sini apa? Draw a plot of required and available fan pressure rise as a function of volume flow rate. And this is the volume flow rate, the x-axis, and the y-axis is actually the operating or available head lah. And tapi yang ni kita tengok dalam unit water Okay. So how do we start? Okay. Firstly, kita kena dapatkan poin-poin penting lah. Kan? Kalau kat sini actually dekat soalan tu dia bagi alpha is equal to 1.05. Kalau ingat alpha apa? Correction factor untuk velocity. Velocity adalah velocity of the air yang masuk ke dalam fan tu lah. Okay, yang dalam piping system tu. Okay, so based on given air at 25 degrees Celsius, kita ada kinematic viscosity and density of the air and also some value on the atmospheric pressure. So yang ni value constant based on temperature at 25 for air. Okay, yang ni pun in actual questions, don't worry, this is all will be given lah. Okay, so if in tutorial might not be given sebab benda-benda ni actually constant as you can get from table in the internet lah. Okay, so how do we start this? What we need to do is that we need to find the H required. Okay, this is the minimum value kan, the H required. So using the formula is based on Bernoulli or energy equation at point 1 and point 2. Okay, so jangan lupa kita ada point 1 dekat sini, point 2 dekat sini. Point 1 dekat luar, dekat udara kat luar sebelum masuk hood, jauh kan. So point 2 adalah dekat exit dia. Okay. Okay, so the differences in pressure, velocity, elevation and total loss. Okay, yang ni standard equation. Okay, so from here kita boleh reduce this equation based on information given ataupun the situations in the questions. Okay, so kita go through sini. Based on this equation 1, actually kita boleh ignore the airspeed at V1. Since at point 1, it is far enough away from the hood inlet. Okay, so kalau kita tengok dekat gambar ni, V1 kat 1 ni dia terlampau besar. So kita boleh consider dekat position 1 ni, V1 dia equals to 0. Dia sama juga case macam case sebelum ni lah, bila kita consider tank kan. Kalau kat sini masuk dia punya pipes lah kan. So if let's say point 1 dekat sini kan V1 equals to 0 sebab tank ni sangat besar, and then dekat sini dia punya fluid almost tak bergerak. So same situation here. So udara dekat 1 ni sangat jauh, and then dan kat sini is considered no velocity. Yeah, that's why untuk this question V1 actually kita boleh cancel out. And then another one is at point 1 juga, pressure 1 is atmosphere kan, dekat luar kan. So P1 equals to atmosphere, which is 0 lah, kita consider 0 So that is why untuk sini kita boleh cancel out P1 juga kan. However dekat P2 pula kita kena consider P2 pun to atmosphere juga, but at the same time dia ada rho G H, in which H equals to Z2 minus Z1 sebab perbezaan ketinggian Z1 and Z2. Okay, so dia kena minus. Okay, kalau kita tengok dekat sini, rho ATM, the atmospheric pressure minus the rho G Z2 minus Z1. So kita replace dekat sini lah actually. Sebab PATM dengan PATM kita dah cancel out. So dah tinggal dekat sini rho G Z2 minus Z1. Okay, so sini minus lah. Okay, so since rho G and rho G boleh cancel out, so hanya tinggal minus Z2 minus Z2 minus Z1. So actually this term and this term can further cancel out kan. So the elevation dah di-consider lah dekat situ. Okay, so in the end kita akan reduce the required net heat atau H required equals to yang ni sahaja. Okay, and from here actually kita boleh break down the losses, head loss, total head loss, in which kita kena consider the major losses and minor losses kan. Major losses lebih kepada friction kan, that's why dia ada friction factor kat sini. Okay, minor losses ni dia ada banyak benda. Okay, so in this question means that kita start dengan benda ni dulu, how to settle out this second terms in the required net heat. Okay, kita kena consider major losses and minor losses. And actually untuk major losses, firstly macam mana kita nak settle out? Kita kena dapatkan value of F. And nak dapatkan value of F macam mana? Firstly, kita kena kalau ingat lah, this F value kita boleh dapat daripada Moody diagram. Moody ataupun Moody chart lah. Okay, nak dapatkan Moody chart, kita kena dapatkan apa dulu? kita kena dapatkan roughness factor dulu. Ingat lagi, Moody chart tu macam mana? Moody chart tu, sekejap saya tunjuk dekat sini. Moody chart. Yang tu chapter 6. Tak ada dekat sini. Tak apa. Saya rasa korang masih ingat lagi kot kan. Dia ada sini the roughness factor, and then sini adalah dia punya Reynolds, and then di sini adalah dia punya friction ataupun orang panggil dia punya friction factor. Okay, so dia ada graph tu. Ingat tak lagi? Kan? Sini kalau bahagian laminar, bahagian transition and bahagian turbulent. Okay, so based on information given, kat sini dia dah bagi dah epsilon, the roughness is 0.15 mm dengan diameter pun dah diberi 0.23. Based on these two information, kita dah boleh dapatkan this value 6.52. Okay, so yang ni kita dah dapat. So untuk dapatkan ni, kita kena dapatkan lagi satu, which is the Reynolds number. Reynolds number kita tahu ada rumus dV over kinematic viscosity. Kinematic viscosity is this one lah. Okay, sebab air kan. Diameter is given. Velocity is actually not given dekat dalam questions ni. Tapi apa yang kita boleh guna adalah this volume flow rate. So macam mana velocity is related to volume flow rate adalah Q equals to AV, di mana V equals to the volume flow rate over A. Q ataupun V dot lah. Alright. So daripada ni kita replace this V dot over A adalah A dia adalah dia punya area of the pipes lah. 4 over pi d squared. Sebab diameter diberi kan. So in the end kita akan dapatkan this value of Reynolds equals to 1 times 10 to the power of 5. Actually kat sini square. Dia tertinggal square ni. Sebab d squared 0.23 squared. And then kita dah dapat this value. Kita dah dapat this value. Based on these two position, kita boleh dapatkan the value of this friction factor equals to 0.0209. Okay, so actually daripada sini kita dah settlekan untuk major losses sebab kita dah dapat value of F. And then we move on to the minor losses pula. Minor losses. And minor losses ni kita kena refer balik apa yang ada tadi. So kita ada orientation, first orientation, and then kita ada valve. Kan? Sebab kita ada valve tu adalah damper lah kalau kat sini. Dia sama. Lepas tu kita ada entry losses tadi kan. So ada 3 terms yang kita kena consider. In which first the entry losses given kan, KL tadi. Lepas tu 5 kali elbow punya losses and also the damper ataupun valve punya losses. So kita add on semua equals to 4.15 untuk these terms. And then V squared over 2G kita replace balik. Okay, so kita dapat yang ni. So kita masuk balik ini dalam equation. Okay, so kita dapatkan value ni. Okay, so untuk alpha ni pun given jangan terlupa 1.05 kat sini. Sebab kita ada benda ni. Betul tak? Okay, so benda ni dia terkeluar lah kat sini. Okay, jangan lupa sebab yang ni H total je. H total. So kita nak H required. So kita ambil A ni. Masukkan. Oh, tadi saya tersilap So A ni bukan dari sini. Ini adalah dari sini. H required. The required net head. So kita ada this term and this term. This term and this term. Kita replace lah 0.2, 13.4 over 0.23. Yang ni 4.15, ni 1.05. So V adalah dari sini lah. Okay, kita dapatkan value kat sini. So kita selesaikan semua ni untuk kita dapatkan nilai V dia. Kita dapat 6.81. And then kita dapat the value. And the value for, tapi the value yang kita dapat ni actually the required net head of air. 15.2 meter of air. And so kita tengok dekat note dekat sini. Dia kata apa? Sekejap saya ambil highlighter. Note that the head is expressed naturally in units equivalent of column height of the pump fluid, which is air. However, we need to convert to equivalent column height of water by multiplying the ratio of the air density to water density. So yang ni senang je sebenarnya. So untuk convert, apa kita kena buat? Kita dah tahu yang ni. Ni kita dah tahu. Kita darab density of air divide by density of water untuk dapatkan H required for water. Okay. So yang ni dengan yang ni at 25 degree actually dia constant boleh dapatkan dalam internet je sebenarnya. Lepas tu kita dapat equivalent 0.709 inches of water. So means that at operating volume flow rate tadi 600 cubic per minute, actually dekat sini kan, dia kita dah dapat satu point. Sebenarnya point line merah ni sepatutnya kita tak dapat lagi soalan ni yang suruh kita keluarkan actually kan, draw a plot of required and available fan pressure kan. So sebenarnya ini merah ni consider tak ada lagi. So kita dapat point pertama. Point pertama dekat sini at 600 actually kita dapat 0.709. Okay. So kita dapat point ni. So sepatutnya kita kena repeat the calculation at several value of volume flow rate. So means that kita try lah at 200 cubic feet per meter. Kita akan dapat supposedly this value lah. At 400 supposedly this value. At 600 this value. At 800 supposedly kalau yang ni lebih graph dia dah terkeluar lah. So maybe kita ambil beberapa, lepas tu kita dapat this line. Okay. So seperti yang kita tahu, untuk operating point adalah di mana H available and H operating sama kan. So at least this is the minimum requirement kan. So minimum requirement dia sebenarnya 650 ya, dekat sini. Ini bila kita dah dapat graf lah kan. Okay, so at 650 cubic feet per meter. Okay, at which both the required and available net heat is equal to 0.83. Kan, yang ni kan, dekat sini 0.83. So, kita boleh consider that we can conclude that the chosen fan, kan, dia suruh bagi tahu tadi apa? Dia nak tahu fan ni adequate ke tak adequate dalam sistem ni. So based on apa yang kita dapat ni, kita boleh conclude that the chosen fan is more than adequate for the job. Sebab apa? Sebab the purchased fan is somewhat more powerful than it is required, which it yields higher flow rate than necessary. Kan, minimum 600 tapi dia yield 650 kan untuk minimum. Okay, so HA is more and equal to HR. This consideration dah met kan? Sebab fan tu lebih power daripada minimum, which is 600 tadi. So apa yang dia dapat adalah 650 untuk operating dia. Okay, so in the end kita boleh consider dia sesuai lah fan ni adalah sesuai diguna pakai dalam sistem tu. Okay, so yeah, the question is a bit lengthy kan, agak panjang, tapi sebenarnya konsep dia sama je. Kita guna konsep apa yang kita faham dekat chapter 6 dengan additional items, especially on this pump performance curve lah, untuk kita fahamkan macam mana kesesuaian satu-satu pump tu dalam sistem perpaipan tu. Okay, so that is all for chapter 7. Thank you.